introduce ourselves. Yeah, I'm Jerem. My major is computer science, and I have a minor in statistics. And I graduate next semester. I have software development and mathematics.
I'm Tristan Allen, far left. I also graduate next semester. I'm going to be a psych major, industrial organizational psychology, which is like business psychology. And I have a minor in data science, which is hence this class. Um, I love working with artificial intelligence. I'm learning the human factor, which is kind of like how technology and your brain interact and make them as good as possible.
Yeah. Financial economics, which is strong emphasis in statistics and financial modeling.
What is discrete event simulation? So essentially, we talked about how discrete is separate and distinct points, whereas continuous is something continual. But with statistics, something that's really cool is we can essentially create a model where we create separate individual points. It takes a lot less computational power. And what that means is in a cheaper, quicker way, we can model real life things that happen. And so in this case, let's talk about what we're doing. So we're talking about airplanes for simulating the life cycle of a specific part, let's say a hydraulic. And so essentially the goal of this is to say, well, if we have more parts or if we have more space in the depot for parts to get fixed, will that make it so that we have less MICAPs? Will that's kind of our goal for this model. And so that's the use case we're hitting. And some of the other use cases that you could use in the future would include capacity planning. And so maybe we know that increasing space will help, but how much? How much more space do we need? Or how can we optimize our inventory? And we can do all this through discrete event simulation. And it will be statistically accurate based on distribution parameters from historical data and real world constraints. But with that being said, not every simulation can follow real world exactly. There will always be some things that are slightly.
Let's choose the honestly. So this is kind of the different cycle of the depot. So most of the parts are going to start on aircraft in the fleet. Once those part breaks, it schedules it to send it to what's called condition F, where they basically just wait at some warehouse somewhere and wait to be fixed by the depot. Once the depot, it only has a certain capacity of mechanics that can actually work on parts. Once that capacity is open, parts move from condition F into the depot. And then when they're repaired, they move to condition A, which is just like the warehouse distribution system that sends it out to all the different Air Force bases that need parts. And then from there, they're installed in the aircraft. Sometimes parts can't be repaired. So a little bit into the repair process, they're condemned. And so we'll condemn parts and then new parts are bought. The new buy process is kind of a tricky parameter because sometimes it can take just a few weeks. Sometimes it can take years, depending on the manufacturers. If it's manufactured out of business or stop making parts. So that part has a lot of different distribution ability and parameterization.
This is a really pretty visual. I love it.
Yeah, and so essentially for our simulation, we also get results, and they're supposed to equal to the distribution they gave us. So this one, the first one we do a normal distribution, it's just a fleet duration, and as you can see, it's a normal distribution, and these other two, this one's condition F, this one's reactionary to this stage right here, and so then this one, based on the capacity on this one, this will change. So this does not have a distribution. It's just reactionary. Essentially, they have axis parts, so they don't have a 1-to-1 ratio when it comes to parts. This one, when it comes down to the requirements and the parameters, we were hoping to get data. We were not able to get the data. So that was a challenge for us to build a model we didn't know what the data looked like. So we had to play around with some of the parameters to try to figure out, okay, what can we do to see if this model actually plays out. And when it comes to this model, it has a couple of different parameters that you can choose, and essentially allows us to move things around and see how things will react. So then we'll choose different depot capacities, which is the amount of parts that can be in the depot stage, or we'll choose different amount of parts. We're just moving different parameters to try to figure out which one's like, okay, this will work out. But then as we got closer towards the end of the semester, then we got more closer parameters, values that we can use. And so then later on, towards the end of the model, we'll say it's more like a stretch for us that we did is that we tested. Now we do this into basically, we have our model and we just throw it into a loop to try to find like the best scenario, but that's more like a stretch. But in this one is we have our 15 of these, and we'll just change them to see what fits what and what happens when you change different ones. This also allows to like say one day or people where you fix the parts just burns down and you have like three of those, so that's like 33% of your capacity. What's going to happen to your fleet of aircraft if you lose 33% of your capacity to fix critical parts for the aircraft? And so then you can simulate that, like what will happen if those facilities breaks down, like how many aircraft will be out of service, how long are they going to be out of service?
The idea of the system, we'll do a live demo. The demo has multiple configurations that will be easy for a non-technical person to use. They have inputs they'd like to test. And then with those inputs, they'll be able to see if their target is met or not. And then essentially what we're doing is we're just tracking the different events that happen in the simulation. And then we're generating visuals that you can give to leadership so that they'll be able to determine if they should buy more space, if they should buy more parts, and be able to make decisions like that.
Is it actually unclear that that's a graphic and not code to be like read?
Well, I know what I'm looking at, so it's hard for me not to see it as you're but it's
It's like should we change that graphic?
I think if you're worried about it, maybe what you could do is you could zoom out your VS Code screen a little bit first, so you get more code in there, so you get more
so you
gibberish,
can't read it.
and then make the screenshots smaller.
I think it looks nice, but
I do think it looks nice, and I think those people like trying to read it though, especially developers, I'd probably zoom it out and take a smaller screenshot.
Because it is the same size as the actual text. So when you said that, I was like, oh no, obviously a graphic. I was
But
like,
now I'm
it's
reading
not.
that because it's big enough to read. It doesn't look like a graphic. It makes me want to read it.
Yeah.
Right.
Yeah.
I just was gonna say I thought it was a graphic. I didn't.
yeah, I think it looks 13.
Awesome. So one of the awesome parts about this simulation is that there's a lot of custom inputs you can use. We were given a pretty small requirement of what inputs were needed, and we were able to go a lot farther than that and allow just really in-depth customization so it can be a more realistic simulation. As you can see on this graphic on the side here, this is actually a snippet from the actual simulation of some of the inputs you can put. The total parts, the total aircraft, how long you want to do it for, how long this is kind of the warm-up period to get the simulation primed and the cool-down period so we get accurate data rather than just like some data that's chopped at the ends. We're able to do a lot of different things to be able to be as realistic to the actual life cycle process as possible. We actually also added this feature that allows for custom simulations, so you can choose different aspects like changing the depot capacity by an increment and running multiple simulations and comparing them on the same screen. So you can see what it looks like when you have a depot capacity starting at 20 all the way up to 100 and how that affects all the different stages. You can do that with part count as well. Yeah.
About that is, but let's actually hold comments because there's a whole bunch of these things that might be irrelevant in a minute.
Can I mention one thing real quickly? One thing that we mentioned with the event, and that is very impressive, is that from going from Canvas data frames to real event-based simulation, the simulation time cuts from like 30 minutes to like less than a minute, based on the size of the simulation we're running. And that could be over 100 different simulations with thousands of parts each.
And with it working like my PC at home, you can run thousands of parts, hundreds of aircraft for years at a time, and it will run in under 10 seconds as well.
So this isn't hosted on the Cranebase or anything.
It is hosted on Streamlit actually.
Okay, so then this is
Is that my graph?
yeah. This has three different variables that are changing. So one of them is the number of parts. The second one is the depot capacity, and the third one is because Tristan mentioned how parts sometimes it could take 2 weeks to 2 years, and so then in this one it also affects because part overlag actually has a huge effect on mine cap aircraft. Because when a part is condemned, then depending on the time it takes to receive the part, then that affects mine cap aircraft, which has anything unrelated to deep capacity, but if they have parts, then they don't have to worry about it. But one other thing to consider is also they did mention some of these parts could be really expensive. So then having them in stock, it's when you don't really need them, it's not really ideal. But also when you do need them, you need to have them. So then essentially what this one does is, like was mentioned, each of these is, this is actually like around 400 simulations. So there are 400 simulations and each of these points. So for example, in this one, the total parts is using it. My cap is spark count since it's part over lag on this line here. This one includes the best depot capacity value. So this one's including the best depot capacity, which if we go off the presentation, I can show you guys like what those results look like, and it's just a really long list, but essentially it's picking the best depot capacity, and then when you come to this one, it's choosing the best part combination for this one.
Wait, okay, so you say depot capacity on the x-axis?
It's essentially where they fix parts, the space, and then so in the workstation they have to fix parts.
So there's no impact.
The impact goes, I think the impact, what happens is,
It's based on the lag period.
oh, yeah.
So in this one, what's happening with this one here is we need to change our parameters because basically what we find here is that this depot value right here is essentially being, because since it's choosing the best part combination, it's always maxing out first the best number of parts, which is why in depot capacity you don't really see a difference because it's always choosing the max number of parts in the simulation. So it's not going to go and switch. And once we do the last simulation, we actually just compare like people in parts count.
Like for example, the number of total parts, it can be an infinite amount. So there's no ceiling that they get stuck at and bottlenecked at. But the depot capacity, since it's a set amount of capacity, that's where the bottleneck happens, and that's where you see the giant difference from the lag.
What affects the lag again? Like, too detailed right now. Like, what's the next slide? How much size do you have?
A 5 second
Like
for
two.
the lab. Imagine buying a $5 million part that you need in a month that has to go through 3 years of verification by the government. You get it in 5 years.
Again, just showing the time situation, hundreds of aircraft plus thousands of parts, less than 10 seconds. Good computer, it handles large fleets and handles their needs. That directly from Adam, that's the person who's helping manage just what it needs to be able to compute. We also have comprehensive documentation because they're going to be taking our program and remaking it on their own server. So we have very, very thorough documentation. This is actually the advantage of them coming to us rather than like someone else who keeps their documentation proprietary. It actually just one of the biggest pluses. Also, real quick, again, is that code distracting? That's like